Hey everyone, I'm Nguyen-Tu, and this is Lab 2 of Physics 2211. The purpose of this lab is to analyze the motion of an observed object that has dropped from rest and affected by the forces of gravity and drag with physics principles in a computational model. In this lab, I will be using Newton's second law and the momentum principle. Newton's second law is force equals mass times acceleration that tells us the acceleration of an object is directly related to how much force is applied to the object. The momentum principle tells us that in an isolated system, momentum is conserved for any interaction between two objects. Incorporating these two physics principles in my model with the velocity update formula, obtained by dividing both sides of the momentum formula by the mass of the object, I can predict the motion of my chosen object over time. To complete this lab, I will be following 5 steps. First, I will record the motion of a crumpled paper ball falling downwards in the negative y direction. Second, I will import the video into the tracker software and track the position of the ball at set time intervals. Third, I will edit starter code in GlowScript to model the ball's motion only affected by gravity. I will repeat that step in step 4 to model the ball's motion affected by both gravity and drag. Fifth, I will compare the recorded ball and both models' balls on the same position time graph. After these steps, the main result of my lab is that there is evidence that drag influences the paper ball, but its effect is minimal during the observed time interval with a proportionality constant of approximately 0.0007. Shown here is tracker analyzing the recorded paper ball video for this lab with the pink perpendicular line showing the x and y axes of the chosen coordinate plane and the red dot showing the ball's position at each key frame. In the observation video, the system is the A4 printer paper ball and the surroundings is the kitchen, mainly the floor. From tracker, the initial conditions are position being 0.000774 meters in the positive y direction, velocity being 0 meters per second in the positive y direction, and time being 0 seconds. For the assumptions used in Model 1, I assume that gravity is the only force acting on the paper ball, with air resistance having a negligible effect. On the other hand, I include the effect of drag in Model 2 under the assumption that the force of drag is always opposite to the direction of motion and that its magnitude is proportional to the square of the ball's speed. Shown here is the GlowScript VPython code behind the models for this lab. I have 3 variables that stores the ball's current position, trail, and origin, respectively colored blue, green, and yellow in both models. I also have 2 variables that stores the error representations of the force of gravity and drag respectively colored orange and cyan. As for graphs, 2 are created being a position time graph and a velocity time graph. In this section of the code, the system properties and the initial conditions of the observed paper ball are assigned in code. Of note, the mass of the paper ball is estimated to be 0.005 kilograms from Google. The ball's position and initial velocity are both in vector format, with the y component being the second number in their respective vector. The change in time is set to 0.0167 seconds, the change in time between each of the recorded measurements from the observation video. At the bottom, the proportionality constant for the magnitude of the drag force is assigned to 0 for Model 1, so that only gravity is affecting the model, and 0.0007 for Model 2, so that the effective drag aligns with the last recorded observation. This section of the code is the same for both models. I'm estimating the position of the model ball at each of the time intervals that the paper ball in the observation video has data recorded with a while loop. Fnet is set to equal the sum of the effective gravity and drag, where drag is set to 0 in Model 1. The force of gravity is calculated by multiplying the mass of the ball by g, the magnitude of acceleration due to gravity near the Earth's surface, or 9.8 meters per second squared. The force of drag is calculated by multiplying the proportionality constant b with the magnitude of the ball's velocity squared as stated earlier. The ball's velocity is updated with the velocity update formula to calculate the change in velocity after each change in time. Similarly, the ball's position is also updated by multiplying the calculated velocity by the change in time to get the ball's change in position and adding that to the ball's previous position. Time is updated by adding the change in time to the previous time. As these prediction calculations are made, the model ball's trail is updated to reflect the calculations, and the calculations are recorded into the position time graph and velocity time graph. Also, the values for time, ball position, and ball velocity are printed to the console for easy transfer to Google Sheets for the analysis. Shown here are the resulting models with Model 1 on the left and Model 2 on the right. Plotting the position time graphs of the observation and the models on the same graph, we can see that the paper ball starts showing the influence of drag after around 0.45 seconds, when the observations start deviating from Model 1. Before then, the position time graphs for the observation and the models are essentially the same. In this lab, 2 possible sources of error are that the camera may have been slightly tilted upward, evident by more ceiling being in the frame than the floor, and the recorded center of mass in each keyframe of tracker could be inaccurately placed, suggested by the observed x component changing position at a non-constant rate. Both of these sources of error would cause the observed y positions to be inaccurate such that the observations could deviate more or less from Model 1. Now for the discussion part of this lab. Which model predicts the terminal velocity? Since terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down, this means the force acting on the system in the vertical direction has reached an equilibrium of 0, and we should see velocity becoming constant in that direction. Therefore, Model 2 predicts the terminal velocity since it accounts for drag, and the rate at which Model 2's velocity increases can be seen in the comparison graph to be slowing down and approaching a constant velocity. With the terminal velocity change if the paper ball was initially thrown downward instead of dropped from rest? Shown here is a velocity time graph of model 2 where time is extended in another model where there is an initial velocity of -5 in the positive y direction to represent the paper ball being thrown downward. As evident by the two lines approaching the same constant velocity value, the terminal velocity for the paper ball when dropped from rest and when thrown is the same, but the thrown paper ball reaches terminal velocity faster than the paper ball dropped from rest.